All right, now there are some exceptions to the octet rule sometimes, meaning sometimes electrons will have actually more electrons available to them. Sometimes they'll have less, but that's usually just in the case of boron. All right, so we don't talk a whole lot about that exception. But on atoms that are in the third row, right, here's the third row, and again, we're really only concerned about our non-metals when we're drawing Lewis dot structures. So phosphorus, sulfur, chlorine, selenium, boron, krypton, argon, all of these ones, third row and lower, can have what we call an expanded octet. It can have more than 8 electrons available to it. All right? So let's take a look at some examples. Sulfur hexafluoride. Sulfur hexafluoride. What's our central atom? Let's draw the Lewis dot structure. What's our central atom for sulfur hexafluoride?
Let's see, that's sulfur. Sulfur is going to be the central atom.
That's right. Sulfur is the central atom. And then what do I do?
Put the 6 F's.
Very good. 1, 2, 3, 4, 5, 6. I want to distribute them as evenly as possible, right?
Now, put the, we need to count the electrons.
That's right. We count the electrons. Each fluorine brought how many?
The periodic table is 7th column, 7.
Each fluorine brought 7. That's 42 electrons from the fluorine.
And the sulfur brought 6.
So that's 48 electrons altogether?
Yeah.
How many do I have on my skeleton model so far?
12.
That's good. 12. Now I have, 36 electrons left, right? 36 valence electrons.
Each fluorine is going to need 6.
Very good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. There we go. There's our structure. Let's see. We're out of valence electrons. How are our formal charges?
Let's see. Sulfur brought 6 in the 6th column, and it has right around it 6, so that's 0.
Very good. Sulfur has 0 formal charge. Now notice that it has more than 8 electrons available to that. What do we call that?
Is that an expanded octet?
Very good, an expanded octet. So that's okay for sulfur?
I don't know. How can we tell?
Well, remember, we use the periodic table, and we have to see that it's in the third row or lower. And sulfur is in the third row, so that's okay for sulfur.
Okay.
Sulfur hexafluoride, the structure here, is very symmetrical. Now, we haven't talked much about structure, and we'll talk about it next chapter more. But if you think about an X, Y, and then a Z plane around the sulfur atom, you can see that the fluorines are occupying each of these sides of these axes, right? And sulfur has no formal charge. The fluorines have no formal charge. This molecule, because of its shape, would be suggested to be a very stable molecule, very stable and very unreactive. And in fact, that's the case. You can actually breathe this stuff. Listen to this guy breathe this stuff.
As long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
By several factors, that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that,
and my voice gets really low, although somehow I'm still funny. It's scientific!
Okay, so notice that he could breathe this stuff, sulfur hexafluoride, and it had an interesting property. Its density was different, therefore sound waves travel through it differently, right? Okay, here's some other interesting properties of this sulfur hexafluoride. They're going to put sulfur hexafluoride in a box.
All right, so here's what's happening. There's a gas inside this tank. It's called sulfur hexafluoride. It's a super heavy gas. Sulfur hexafluoride. It it's boring. It's inert.
Somebody asked where it happened.
It's odorless.
Yeah.
So it's normally boring. But here, watch this. I'm going to slowly pull the lid off.
Okay.
So that should be perfect. Gary, would you take a little end off over there as well? You see
Mhm.
that? Yeah.
Yes,
All right. So it feels pretty good. So let's see if we can float the boat. Okay. Ready? So here we go. Let's see if we can float the boat. Stay there, little guy. Tell me that's not awesome. Isn't that amazing?
That is
This
awesome.
Magic
Yeah.
so is that, it's okay. Push it around. It's
That's
okay. So this
crazy.
heavy gas is about 6 times heavier than the air that we breathe. And so I just have it coming through a tube here. And so I'm going to give us just a little bit more so you can kind of see what's going on. Here's what they use it for. Electrical engineers will flood a room or, part of a semiconductor or something with this material because it doesn't allow electricity it doesn't conduct electricity. So here's a taser.
Yes.
So all right, so look. So when I put the teaser down inside here, watch this. When I put it down inside, it stops.
It stops working.
And then when I bring it back out again,
Oh, wow.
so they will keep it. So if you don't want something arcing from one place to
Doesn't
another.
conduct
But the coolest thing is this:
Right.
because it's inert, you can breathe it, and you might see something different. Ready? So
Can I go first?
So just stick your head way down inside and breathe in. Breathe in. Ready? Now talk to the nice people. Try it. Come here. Get in there. All right, so
All right, so they go on to breathe a little bit more. But what I want you to note is that, first of all, we have a octet there. Second of all, from the Lewis dot structure, we could predict that it's relatively stable. The electron density is on those fluorines for the most because they are highly electronegative, but they're symmetrical. The symmetry of this molecule makes it, you could predict that it would be unreactive. All right, so let's draw some extra expanded octet electron dot structures. Okay, so here are some for the folks at home. Let's do these first two first, and then we'll take a stab at this third one together. All right, so everybody at home, you try to do the first one, and if you want to try to do the second one, if the first one comes easy. If the first one you don't get, maybe you should just stop there and listen to Fred and I do it. And then we can try the second one together. All right, push pause, give it a shot. All right, Fred, the first one. What are you thinking?
I'm not sure what the central atom should be.
Very good. It's a difficult thing to know. What should our central atom be? Either xenon or oxygen, right?
Yeah, what should it be?
Well, the rule is generally you go for the atom that is least electronegative, because the central atom is going to have to do a lot of sharing. And if you're electronegative, you generally don't want to share. So least electronegative is where you would go. All right. Do you know where the least electronegative one is?
Let me see oxygen is more electronegative. It's one of the three. That's right. So xenon is least electronegative.
Very good. Xenon is least electronegative. What do you think, therefore, we should do? Draw xenon in the middle.
Yeah.
And then oxygen, and then the fluorines around like that, something like that.
Yeah.
Now let's do this really quick. Let's just say I had done something incorrectly and decided I was going to draw the oxygen in the middle. There's another way that I could tell that this structure is problematic. Oxygen has an expanded octet. Do you see that?
What does that mean?
It has more than 8 electrons available to it.
Oh, yeah. Okay, is that a problem?
Well, I'll let you tell me. When can an element have an expanded octet?
Oh, it has to be in the third row or lower. Yeah, so oxygen can't have an expanded octet.
Very good. So that's another way we could have known that oxygen can't be the central atom. Okay, so we have xenon as our central atom. Let's add up the number of electrons there are. Now, if you had trouble at home finding the central atom, and you've got this far, stop here and try to see if you can go further by yourself and then come back. Okay? Always good to push stop whenever we're working on problems. See if you can work on them yourself and then get the help, follow-up help after you've tried it. How many valence electrons, Fred?
We got oxygen brought 6, xenon brought 8, fluorines brought 7 times 4, 28, so that's 36 plus 6, that's 42.
All right, 42 electrons. Hope you added those up right. How many electrons do we have on the board already?
10.
Okay, I already have 10 for my skeleton structure there. So I have 32 left to go.
Yeah, so put more electron density on the oxygen first.
Okay, how much more?
6 more electrons.
2, 3, 4, 5, 6. Now it has 8 available to it. Is that right?
Yep. And then do that same thing for fluorine, all the fluorines.
All right. So I have 32. I just used 6. So now I have, let's see, 26 valence electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. Like that. Now I have 2 more electrons. What am I supposed to do with those?
I don't know. What do you do?
Well, whenever you have extra electrons, it's a good idea to put them on the central atom.
Okay.
So I'm going to put 2 electrons on the central atom. Now I have no more electrons, all out. Now I can look at my formal charges and see if my structure looks good. All right, everybody at home, try to do the formal charges by yourself and then watch Fred do them. Okay, what's the formal charge on the fluorine here, Fred?
Well, it brought 7 electrons because it's in the 7th column in the periodic table. So 7 is how many it brought, minus it has right around it.
1, 2, 3, 4, 5, 6, 7.
Yeah, right around it 7. So that's 0.
Very good.
All fluorines have 0 formal charge.
Excellent. How about this oxygen?
That oxygen's a problem. It has a -1.
Ah, okay. -1 formal charge. And this xenon?
Yeah, that has a +1.
Yeah, it brought 8, and it has 1, 2, 3, 4, 5, 6, 7. So a +1. So an indicator that what? When we find formal charges, what's that an indication of?
The molecule's not right.
That's right. But we need to bring more electron density where?
Towards the central atom and away from the oxygen.
That's right. Too much electron density, not enough electron density. One of these has to come down to form a double bond here. So if that were to occur, then the result would be oxygen, double bond to our xenon, 4 fluorines. Whoops. Good enough. There we go. Oh, 2 more electrons still down here. Does that fix our formal charges?
Yeah, now they're all 0.
Very good. That is our structure there for that compound. All right, SbCl5. This one's pretty straightforward. Try it at home, folks. See what you get. Okay, what are we going to do?
Antimony, pentachloride.
Oh, very good. Antimony, pentachloride. 1, 2, 3, 4, 5. Right? How many electrons were brought to this party? Count them up. Make sure you do that. Make sure you finished all the way through before you watch the rest.
10 electrons from, no, 7 times 5. 35 from chlorine. And then the antimony brought 5. So 40 altogether.
Very good. So we got 40 valence electrons. I got on here 1, 2, 3, 4, 5. 10 valence electrons. 30 left. 7 on each of these. Is that true?
Yeah, that's right.
Not 7, but 6. 7 total. So I just used up 6 times 5. Oh, that's 30. I'm done. Am I okay?
I think so, because antimony brought 5. It just wants 5 around it like it has. So no formal charge on antimony or the chlorines.
Very good. Finished. Excellent. Now, let's take a look at how we draw a formal, or actually, let's stop here. Next time we'll talk about this one here. Take a break.